The next thing that we want to define is the gradient of a function f. So we'll denote this grad f of x, y. That's the nabla symbol, but we'll read this as gradient f of x, y. And the gradient of f of x, y is just this vector. It's the vector whose x coordinate is the partial with respect to x of f, and the y coordinate is the partial with respect to y of f. So for example, e.g., if f of xy is equal to e to the xy, then fx in this case is y e to the xy, fy is equal to x e to the xy, and the gradient del f, or rather nabla f, the gradient of f, is going to be y e to the xy, comma x e to the xy. I might be interested in knowing, for example, what the gradient of f at a point is, for example, maybe 0, 0, and then that will be, I guess in this case, very not interesting, 0, 0, for example, but plugging into my functions, plugging into each of my coordinates, the x and y coordinates of the point that I'm talking about. So some things to note about the gradient. We're going to be talking a lot about the gradient in the next section. But maybe just to give you an appreciation for what this thing is, at a point, the gradient of f at p gives the direction of the steepest instantaneous rate of change. Instantaneous rate of change of f. And the magnitude of this thing is the magnitude of that change. Okay, so we'll be playing with this a little bit more as we go along, but maybe just to give you an appreciation of what the gradient might represent, it gives the direction of the steepest instantaneous rate of change. It combines information about fx and fy and gives us an idea of the direction that I would have to go in to get the steepest ascent.